Hello everyone, today we're going to do the DC machine experiment. So our board is a DC machine. For the first part in our experiment, we are using permanent magnet rotor, including the south and north pole. So the first part, you can see that if I leave it it doesn't matter which way I put the magnet in, it's gonna face the poles. So south and north are gonna face this way. So if I just move a little bit, first of all, I see a resistance, doesn't allow me to go more than this unless I put more power. But you see that you can see what happens, and you have to explain in your lab. And then if I try to push more power, so when it comes here at 90, when they are not facing the pole, if I leave it, you saw what happened. Again, I repeat, you saw what happened. So now the question is that does it matter if, like, how much force I experience if the north is up? So the force that I experience is similar to this one, because for you guys there's no way to feel the force that I feel here, so I'm just telling you that is the same. So the force would be the same no matter if the south or north poles are up or down. For the next part, and the direction, oh, I forgot to talk about the direction. So if I put this one up there, you saw the direction, what happened? If I put south pole up, you saw the direction. Okay, next part is asking to connect the exciter windings to 15-volt power supply. So I have to use a jumper, as you can see in the picture on your lab manual. And then I'm going to connect the 15-volt is connected to one side of the exciter windings, and then the ground to another exciter windings. So now the question is asked that what happens? Is there any torque generated? I can see that the torque is more here. Now that I connected, I have to push more force to be able to move it. There is a huge resistance on it. When the permanent magnet rotor is aligned perpendicular to the excitation field, so when I do this one and I'm going to release it, I do it with the other one, like the north pole up, and I release it. Okay. If I just get closer to the other pole, so one of them is closer to the other pole, and I leave it, again this is closer now to the pole on the right side, and I leave it. So you know that the answer, that does it matter to be closer to one pole? Is the direction toward the one to the closest, or no? Okay. Now it's asking to put the blue pole up, so blue pole up, and then I release it. Okay, now I'm going to put the red pole up and release it. So now it's asking to change the terminals, so I'm going to change, like switch the terminals. Plus and minus would be different. So now I'm going to leave it on the top and release it. Again, leave it on the top. So north is up, release it. When the blue pole is up, I'm going to release it. Again, blue pole up, release it. So you can answer the question now using the observations that you have from this experiment. In this experiment, we're going to connect the rotor in a shunt wound machine. You can see the diagram in the video or on your lab manual, the way we connected the field and the armature. So I'm going to apply the voltage 15 volt as requested by the manual, and you can see what happens to the motor. I'm going to stop the motor now. In next experiment, we are going to measure the speed. In order to measure the speed, we are using a tools which is called a stroboscope. So the concept of stroboscopes is coming from the fact that we have a flashing light. So you can see that our stroboscope is actually has a light at the end, that if I connect it to the analog out of our unit interface, then I can apply a signal to it, to like it's basically a square, like a pulse, and that pulse is gonna make this LED light to flash. So if the speed of flashing light is synchronous with the speed of the motor, then it means the frequency of the pulse applied to the stroboscope is matching the speed of the rotor. So in this way we can measure the speed. So the first thing I do, I run the interface for a stroboscope. You can see it here. I set it to 30 Hertz, so it would be a flashing pulse of 30 Hertz. You can see the 30 Hertz is equivalent to 1800 RPM. Just simply 30 multiplied by 60 is 1800 RPM. So what I do, I'll turn it on. So the moment I turn on the stroboscope, you can see that the light is going to be on and it's flashing with 30 Hertz. It's a little bit difficult to see it because it's 30 Hertz, but you can see the flickering in there. And then I'm going to run the motor. So the motor started to run. Now I'm going to aim the stroboscope at the rotor, and you see that the moment that I aim the flashing light to the rotor seems to be like visually with less, like rotating with less speed. But because it's not still in sync, I have to go and change the frequency. So I'm going to increase the frequency a little bit here. So going to above 30 and see what happened. I can see here almost is not rotating, or the direction at some point starts to go back. So I'm going to just go a little bit lower now. Okay, we don't have to be very picky as long as the rotation of a speed goes very low. Here to me is 30.8, which is 1848 RPM. So I'm going to stop the motor here. In next experiment, which is the brush shifting, I'm going to change the position of carbon brushes. So if I put the holding bar for the DC rotor in different holders, so you can see that there is a holder at 0 degree, there is a holder at 10 degree, there is a holder at 20 and minus 10 and minus 20. So if I remove this one and put it in the holder, so I'm going to put it, for example, at 20. In this way, the rotation of the carbon brushes is going to be changed compared to the exciting voltage. And we're going to see how this is going to affect the speed of the motor. So I'm going to run the motor, and I'm going to turn on the stroboscope, and I'm going to aim to it. So the speed was 13.8 Hertz or 1848 RPM before. Now it seems that it's not quite in sync. So actually maybe a little adjustment might. Okay, here around 1824 it seems that the speed is very low, and you can see even the the windings. So the speed gets so slow. I can go even lower, and here you really can see that I can clearly see the windings even just shaking around the point. So here the 1764 is the exact speed. Then I stop the motor and I'm gonna remove it, and we need for like higher uh, we need for higher degree, but because we don't have the holder, so I'm gonna just manually change it. So the first thing I do, I hold this one and I'm gonna, so after I turn on the power, I can see that the motor rotates, but when I go on higher degrees, it literally stops. So anything after, I would say 50, the motor doesn't rotate after 50 degree. Next experiment is armature voltage. So I'm going to apply different voltages to the armature and measure the speed. We start from 20 as requested in the table. So I'm going to turn on the motor. You can see the motor started working, and set the power. Before showing you this, I try to play it myself a little bit to find the right value. I'm going to show you at 40-80 RPM, and you may not be able to see it properly in the video because of the the video effect, uh, but I can see that the lines are pretty much stopped here, and I can see the lines, and that's why we can say 4080 is the RPM for 20 volt. Now I'm gonna stop it and go to, so 4080, I'm gonna fill up the table 4080 for this. For 18 volts, so I'm gonna go lower to 18 volt. I just again played with some number for that, and I get around 3580. So I'm going to show you the 3580 that I reached at almost here, 3570. So turn on the power, and again you can see, I don't know if you are able to see it in the video or not, but I can see the lines on the rotor, so that tells me that this is the sync RPM for 18 volt. So I did the same thing for different voltage. I'm going to show you also for um, 16 volts. So for 16 volt, I got 3080 RPM, and for 14 volt, I got 2460 RPM, and for 12 volt, I got 1960. And so as I promised, I'm going to show you for 16 volt as well, which is around 3084 RPM. So again, I can see the lines moving very slowly here, meaning that the speed is almost in sync here. So the RPM for 16 volt you can claim to be around 3084. Next experiment is rotation direction. So for this experiment, the voltage applied to the to the exciting like exciting field, I'm gonna just switch the positive and negative. So the one on the left now is connected to the positive, and the one on the right is connected to the negative. So I basically changed the polarity of the field, and let's run it and see what happens. So direction now is clockwise, as you can see, and now I'm gonna stop and change this to here. So I change it back to whatever it was, and you see that now is counterclockwise. So the rotation went from clockwise to counterclockwise. So the next experiment is braking experiment. We want to see how the braking run down and run up works on the DC motor. In order to do that, we have to make some connection. So we have some relays on the USB interface module of the unit range system. And for this one, these relays are controlled by switching from one page on LabSoft to another page. So we have a page for example, braking. It changes these relays and these switches so that it reverses the power and then it does the braking. So these relays are basically working for us to do different functions: run up, run down, and braking. Um, so the first thing that we do, also there is a current board here. The small board on the top is, we call it current resistor board. So the whole concept is that because the unit train cannot measure the current directly, we run the current through a resistor board, which is this small board here, and then if a current passes through a 1 ohm resistor, the voltage is equivalent to the current based on the Ohm's law. So we measure the voltage. Basically, it means that we are measuring the current. So this is the way that unit trains measure the currents. And we are connecting the voltage, like the armature voltage here is going to channel A oscilloscope, and the current on the resistor board is going to channel B of oscilloscope. So channel A is measuring the voltage and channel B is measuring the current of the armature. So now the first thing we do, I'm going to power the motor, and you can see that the motor started running. I'm going to turn it off for a second and set up the oscilloscope. So I'm going to click on the oscilloscope and do the settings that we need. It's asking to set the channel A for 5 volt. It is already 5 volt. DC, it's already DC. Channel B to 500 millivolt. It is already 500 millivolt and DC. The time base is 200. I already set it up to 200 millisecond. And it is asking to set the trigger to channel A. So trigger menu panel is here, channel A. Falling edge, this is the falling edge. This is the rising edge, so falling edge. And then it's asking to set the trigger to 13 volts. So there is these arrows here that move this trigger level up and down, which is marked by this plus, because trigger is on channel A and channel A is 5 volts, so 13 volt is almost 2 squares and a half. So I'm going to increase it a little bit here. So this is almost 13 volt trigger. And then the 25% is the like pre-trigger level. So what I do, I'm going to again just run it. And the moment I click on this is normal operation, I click on run down, let's see what happens. So the first thing that we saw, oh, I missed it, so I have to do it again. So let's set it to single. Okay, so normal operation. So I'm trying to catch the moment when the rundown happens. So when I click the rundown, first of all, the motor stops, and then we got the trigger here. So you need to like draw this or capture this and put it on the Word file. There are different ways of doing it. Either you can sketch it on the oscilloscope on the Word file, like on the Word file where the oscilloscope graphs are supposed to be copied paste, or you can take a screenshot from the video and put it there. It's up to you. Make sure only you just explain what's happening here. Look at the 5 volt, 100 millivolt, which one. So the blue one basically is channel A, and channel A is the voltage. channel B, which is the red one, is current. So you need to explain what happened when we did the rundown. So I'm in rundown. I'm going to click on run up, and you can see the motor started running again. Now I want to see what happens if I click on braking page. You saw that the motor brake, and then this is what happens. So again, you need to explain on your mm, lab report. First of all, you have to somehow capture this either from video or just manually sketch it on your lab manual, lab report, and explain the difference between rundown and braking, both in theory and both in practical in the lab. Next experiment is the connection in series wound machine. So you can follow the diagram from the manual, or you can see the diagram here on the video, how the windings are set up in the series wound machine. I'm going to turn the power, set the voltage to 16 volt, and you can see that the DC motor started running in the new configuration. So next experiment is about the armature resistance. So the way we hooked up the circuit together, we are actually using an onboard 6.8 ohm resistor in series with the armature voltage. So when I run the motor, so you can see that the motor speeds speeds up. And now what I'm going to do, I'm going to use a cable to short this resistor. So one side of this cable is now connected to one side, and the moment I connect, let's see what happens. I think you heard the higher noise from motor, which is an indication of, you need to explain indication of what, but definitely the noise for the motor got more, so I think you should be able to answer the question in the lab, that what happened after I short the 6.8 ohm resistor, which was in series with the armature. That's the end of the lab. I hope you guys were able to properly see all the steps of experiment. Again, it's a video, so I did my best to make it as clear as possible, but sorry if there were some uh, parts that were not quite clear because of the limitation that we had in the lab here. Okay, thank you for watching this video.